Hello, everybody, and welcome to the pre-lab lecture video for experiment 3, which is called Studying the Density and Miscibility of Liquids. All right, so the objective of this experiment is to first determine the densities of 3 different unknown liquids, and then we will test their miscibility with each other and also with water. So you can see here, this is a picture I took of the 3 unknown liquids that are all in distinctly separate layers, forming what we call a density tower. Okay, so let's imagine a scenario to start out with. Let's say you have a vial of an unknown colorless liquid, and it could be one of seven possible colorless liquids that are surrounding it, right? So basically you have 7 knowns that it could possibly be. You don't know which one it is, and it's a totally colorless liquid. So how would you figure out which one it is? Maybe give you a second to think about that. Right, so it would be, you can't just kind of look at it, right? They're all colorless liquids. So we have to kind of think about, okay, what else can we do? And so one thing we can do is basically use observable or measurable physical or chemical properties of matter to distinguish them, right? So for example, we want to talk about properties of matter. One is color, but we said they're all colorless, right? So that's not particularly helpful. Since they're all liquids, we wouldn't really want to measure the melting point, but maybe the boiling point, right? We could see at what temperature do the different liquids boil, and that could help us figure out which one it is. There are other properties as well that we could look at. Are the liquids conductive of electricity? When we're talking about solids, we might talk about their texture, but a liquid, we might talk about its viscosity, which basically means sort of if you were to swirl it around, how thick is it, right? Versus, the thinness or the movability of the liquid. You could also talk about miscibility, and we're going to talk about what that means, but basically can you mix it with another liquid, right? Will the 2 liquids mix, or will they form distinct layers? You could talk about density, right? Density is a measurable physical property, and so you could weigh out a particular portion of it, also measure the volume and calculate the density and see if it matches any of the known substances, right? So we're looking at all of these properties of matter. So we want to talk a little bit about the different properties of matter. So first off, there are what are called physical properties of matter and chemical properties of matter. And in physical properties, we're not changing the identity of the substance. So the chemical remains as it is, the same chemical. If we were looking at chemical properties, we would be studying its reactivity to convert into a different chemical. And that's one thing we could have done, right, or thought about doing with our unknown liquid. See if it reacts with other things, like does it react with acid? Does it react with base? Does it react with water? Right, those are chemical properties that we could observe in the unknown and the knowns to help us figure out which one our unknown might be. But if we didn't want to actually change the identity of the substance, we might look at different physical properties. Some physical properties are called extensive physical properties, and others are called intensive physical properties. And basically the difference is whether or not the property depends on the amount of the substance, right? So for example, if you had a rock and you measured its mass, well, it would the mass of the rock would depend on how big the rock is, right? And also what it's made out of. But, so certain things like that where it depends on the amount, right? That would be an extensive physical property. But there are also intensive physical properties that don't depend on the amount, such as the color, the density, melting point or boiling point, right? Those don't change if you have a different amount of the substance. All right, let's talk a little bit more about density. Density is defined as the mass of a given amount of something divided by the volume, right, that substance takes up. So it's a physical property of matter, and it's an intensive one, right? And it expresses the relationship of mass to volume. So the more mass an object contains in the same given space or volume, the more dense it is. And we can measure density. For example, we did that in a previous experiment with a cube, right? You can measure the mass of the cube, and they're showing you a picture here where they're doing the same thing. Let's say this cube weighs 240 grams, right? And then you can also measure the volume directly or with a ruler, or indirectly through volume displacement of, for example, water. In this case, the dimensions of the cube are known, right? So it was, the volume was calculated directly, length times width times height, right? And we got 3 times 4 times 5, all in centimeters, would give 60 cubic centimeters. So taking 240 divided by 60, it gives us 4, with only 1 sig fig, because only the 6 here is significant, right? And then we say that the units are grams over cubic centimeters, which would also be the same as milliliters, right? So that is the density. It's just one number, not two numbers, right? But the units are grams over some unit of volume. Could be cc, which stands for cubic centimeter, or just, you could write that the same thing with cm to the power of 3, or milliliters, or any other unit of volume. Okay, so we also want to recognize that density is a conversion factor, and it can be used to convert between mass and volume if it's known for a particular substance. So let's see an example of when we would use density as a conversion factor. So the example problem is 50.00 liters of ethanol will have what mass, right, at 20 degrees Celsius. So it does depend on the temperature, but that's just room temperature, right? So they just kind of added that in just to make it super clear. So here's a table that provides us the densities for various substances. Notice that ethanol is on the list here, and it has a density of 0.789 grams per cc, or cubic centimeter. So remember that that relates the mass and the volume. They've given us in this problem a volume, right? 50.00 liters is a volume, right, of a liquid. So we can start with volume, use our conversion factor of grams over that volume, right, to get to the mass. The problem is that this density is given in grams over cubic centimeters, and our volume is given to us in liters. So we do need to convert the liters through dimensional analysis to cubic centimeters, remembering that that is really the same thing as milliliters. Then we'll be able to use the density to get to grams, right? And it would actually be useful to report the answer in kilograms for the mass, just because it's a rather large volume of ethanol. 50 liters is quite a bit of ethanol, so it's going to be a ton of grams, right? It might be a more reasonable number to just go ahead and report it in kilograms. Okay, so we would set up the dimensional analysis by starting with the number that it gave us, 50.00 liters of ethanol. Notice that I worked on converting liters to cubic centimeters, which is the same thing as milliliters, because there's 1,000 milliliters or cc's or cubic centimeters in 1 liter. I used the density as a conversion factor to convert from cc to grams, and then I converted grams to kilograms so that I would have a number that I didn't have to put into scientific notation because it's a very large number, and I would be worried about getting the right number of significant figures. So it works out to 39.5 kilograms. Let's look at another example calculation where density is used as a conversion factor. Example 2, if a metal object, let's say this metal object down here, this little yellow lump of metal, it's claimed to be gold, right? How could this be verified? Well, one way is to figure out the density of that object, because the densities of different metals are known, right? Here's a table that lists some densities of some common metals, such as aluminum, copper, gold, right, etc. Notice that the density of gold is about 19.3 grams per cubic centimeter. So we would want to determine the density of this, which means that we would want to weigh the piece of metal, right, to get the mass in grams. And then we would want a way to find the volume of that object. Now, this is not a perfect cube where we could measure the length of the sides. So in this case, we would need to do volume displacement. So we would typically get a graduated cylinder, fill it to some amount of, to some volume with water, record that initial volume, add in the metal object, and then record the final volume, right? And then the volume of the object is the final volume minus the initial volume, or the displacement of the water. And then if we set up our calculation where density is equal to the mass of the object over the final volume minus the initial volume, we'll end up with 19 grams per milliliter, which again, noting that that's really the same thing as cubic centimeters. So it does look like this metal object is indeed gold. Okay, so again, density is a physical property, right, expressing the relationship of the mass of an object to its volume. And you can see here that this is another example of a much more complicated density tower than the one that we are making in this experiment. But you can see they have a number of liquids and even solid items, such as like a cherry tomato or a bolt, right? And they have carefully layered each liquid one on top of the other. And the one that is at the very bottom is the most dense, and it would have the highest value for its density, right? So it would have a larger number for density than all of the liquids above it, with the red liquid having the lowest density. And then they just often will color a lot of these layers to make the distinctions between the layers a little bit more obvious. So in our experiment, again, we are going to be measuring the densities of 3 unknown liquid substances. They'll be called substance A or compound A, substance B, and C. So we're going to use a graduated cylinder, take some of that liquid, measure both the mass and the volume of that liquid to calculate the density. So we'll have the density of all 3 of our substances. And then we're going to carefully pour those into a test tube, starting with the most dense liquid, then the second most dense liquid, then the least dense liquid. And here's all the possibilities for the liquids that it might be. We're also going to compare the densities that we calculate with this table to determine what the identity of the three substances A, B, and C are, right? So if we have something close to 0.789, for example, then we might say that that could be ethanol, or look at this one is very close as well, possibly isopropanol as well. But others are a little bit more distinct, right? Between there's nothing else really close to them, right? So you could be a little bit more sure based on that density calculation. Okay, so after we measure the density of our three unknown substances and form our density tower, we're going to be looking at miscibility of those liquids. And so in order to talk about that, first we need to do some defining. What is the difference between miscibility and solubility? Those terms sometimes are interchangeably used, but they really have different purposes and different definitions. And so we want to use those properly. So for this experiment, we are going to define miscibility as the property of two liquids to mix in all proportions, forming a homogeneous, sometimes people will pronounce that homogeneous, mixture. So basically, we're talking about two liquids, and if you mix them together, and you want to give them a good chance of mixing, right, shaking, will they mix together, right, in any proportion, or will they form distinct separate layers? So for example, if you had mixed some sort of alcohol like ethanol or isopropanol with water, right, those two liquids are miscible, so they will just form one homogeneous layer. If you mix oil and water, those two liquids are immiscible, so they will form distinct layers. And because water is more dense, it will sink to the bottom, right? And that's the blue layer here. And oil is less dense than water, so it would float to the top, right? So again, when we're talking and using the terms miscible and immiscible, we're talking about the ability of two liquids, right, to mix in all proportions. We would define that as miscible, and if they did not mix, immiscible. Solubility is going to be defined as the maximum amount of a substance. In this case, we're going to be defining it as a solid substance that will dissolve in a given amount of water at a specified temperature, right? So some solids, for example, sugar, if you mix some sugar in water, right, the sugar will dissolve to form what is known as a solution of sugar water. And other substances, other solid substances such as sand, do not dissolve in water, right? And so we would say that that substance does not dissolve or is insoluble. And then the substance, the sugar that did dissolve, is defined as a soluble substance. So we want to think about whether or not we're mixing a solid, right, with a liquid to see if it's soluble or not, or if we're mixing two liquids together to see if they are miscible or not. And then, so in this particular experiment, we're primarily dealing with miscibility, not solubility. What is miscibility based on? Well, it's based on a couple of factors. It's based on polarity, right? And oftentimes we say like dissolves like. So if we have similar molecules, so they have a similar chemical formula or structure, right? And they're both, for example, polar, they're much more likely to mix than a substance that we would say is nonpolar mixing with a polar substance. That's much less likely to mix. So if they have similar polarity, then they are much more likely to be miscible. For example, water and ethanol are both polar molecules, and they are miscible. Whereas vegetable oil and water are not similar because water is polar and vegetable oil is non-polar. So those are much less likely to mix and in fact do not mix, right? They're immiscible. It's also dependent, if you think about it even more specifically, to what are known as intermolecular forces. So if they have similar intermolecular forces, then they are likely to be much more attracted to each other and therefore likely to be miscible. So here you can see this is an ethanol molecule, right, with some carbon atoms, hydrogen atoms, an oxygen atom, and then one hydrogen directly bonded to an oxygen atom, right? And we can see some hydrogen bonds being able to form between the oxygen of water, this is H2O, right, and the hydrogen of ethanol. So because both water and ethanol can form hydrogen bonds due to having hydrogens directly attached to an electronegative oxygen atom, they have similar intermolecular forces and they are miscible, right? Whereas oil and water, those two chemicals do not have similar intermolecular forces. Again, water can hydrogen bond, but the oil molecules cannot because they do not have hydrogens directly attached to oxygen atoms, right? Instead, they have lots of hydrogen atoms, but they're all primarily attached to carbon atoms, and they're nonpolar. So they form different intermolecular forces. You might have heard of London dispersion forces that are really dissimilar to hydrogen bonding, and therefore they will not be very attracted to each other and they're not miscible. Okay, so after we form our density tower, now we're going to be doing some testing on miscibility. And first we want to test whether or not each of those substances, again, substance A, B, and C, are miscible with colored water. And again, we just make it colored water just to make it a little bit more easy to see. So here are the three substances that are left behind. So notice that I already took some out for each substance to make my density tower. And whatever's left behind in the vial, I went ahead and added some of the colored water to see if it was miscible with the substances. And you can see that in two cases, it was miscible. Just one single layer, right? They formed a homogeneous mixture. And the color is dispersed, right, amongst the entire solution. And in one case, it's immiscible. You can see some bubbles here, but there's clearly two layers, right? There's a clear layer on top and then a colored layer. The colored water is on the bottom. And by the way, this is not A, B, and C. I've mixed those up so that you will have to do your own testing, right, and not just copy what's on here. So, these are in an order, and I very specifically did not show you, if it was A, B, or C in this case. So again, we're first going to look at whether or not the three substances are miscible with water, and we're going to take careful observations and record those in our data sheet. Then we'll add some of the colored water directly to our density tower, and we'll note exactly where that colored water, which layers, right, that it goes into. Then we're going to stopper the test tube, right, shake it up, and then allow the layers to settle, and it can take a long time for the layers to settle, up to an hour. And we're going to then make some observations about what happened after you mixed it, right? Is it still three distinct layers? Have all the layers combined, or maybe only two of the layers have combined, and now you have two layers, right? So you want to take some careful observations of exactly what happened once you mixed those up, right? And think about what substances might have been miscible in each other, forming, one giant layer. And, what data do you have to know which substances those are? Okay, so make sure that you are using your correct PPE, right, for this experiment. This is really the first experiment where we're using chemicals that other than water, right? So some of them are toxic, some of them are flammable, and some of them are irritants. So we want to be very careful and using the correct PPE and safety attire. So make sure you're wearing your lab coat, nitrile gloves, long pants, closed-toed shoes, and wearing your goggles while you're performing this experiment. Okay, let's start with the pre-lab. As always, I suggest you start with the pre-lab, and it's going to ask you to do some reading in your book about density, miscibility, and solubility. It asks you about safety precautions, right, for the experiment, which we talked about. A mathematical expression for density, right, so that's the equation for density. And then it asks you to calculate density, right? So it says a student has collected the following data, right? They have the mass of their graduated cylinder while empty, the mass of their graduated cylinder, and some liquid, right? So we're going to take the difference between those, and that's the mass of the liquid. And then we're going to divide by the volume of the liquid. So it wants you to look here and carefully measure the volume to the correct number of significant figures. Remember that we want to look at the delta value, right, or the increment for each hash mark, and then estimate right in between the hash marks. So make sure that you're reading this right to the correct number of significant figures. And then calculate the density, right? It's going to be one single number, right? And then make sure you include the units of grams over milliliters. After that, we are going to be describing some combination of substances using the following terms: miscible, immiscible, soluble, or insoluble. Right, so think about if you have sand sinking to the bottom of a beaker of water, would you describe that in terms of its solubility or miscibility? Remember, if it's two liquids, right, we're just describing it as miscibility, and a solid mixed with a liquid would be solubility. So you want to describe that as soluble or insoluble, right? Because it's sand, which is a solid mixing with water. So think about all of these scenarios. Ask yourself, what's being mixed? Is it two liquids or a solid and a liquid? That will tell you if you should be using the terms miscibility or solubility. And then if it mixes, right, miscible or soluble. If they don't, then immiscible or insoluble. Okay, and then it asks you to think about if you have cooking oil, water, and a piece of ice in a tall glass, what would that look like? Right, so actually draw a glass, right? Draw the layers. So which one would be water, which one is the oil, and where would the ice go, right? Think about how ice behaves in a cup full of water. Does it sink? Does it float, right? So, think about that and then draw something and make sure to illustrate the different layers so that I know which one is which. And then when you're turning that in, of course, always remember anytime you're turning in a picture of a worksheet to have your ID, right, shown. Okay, and then for the data sheet, that's where we're collecting all of our data and observations. So it starts off with measuring the mass of a 10 milliliter graduated cylinder. We're going to put in some amount of liquid A and remeasure the mass. And the mass of liquid A will just be the difference between those two masses. Making sure to measure the volume of that liquid, right? Bottom of the meniscus, making sure to measure to the correct number of significant figures, and then calculate the density and show your calculation right below the table. After you're done with that, you actually need to pour that into a test tube and clean out your graduated cylinder carefully and reweigh it before you pour in some of liquid B, and do the same thing before you would pour in liquid C. So that's why there's 3 different numbers for the mass of the same 10 milliliter graduated cylinder, because each time you are cleaning it in between, and depending on residual water or something like that, the mass might be slightly different each time that you weigh it. Okay, after you filled out that table and you need to think about the densities, right, that you calculated. Remember that we're pouring in the most dense liquid first, then carefully sliding in the next liquid, right? Don't just kind of like pour it in like that, right? You want to sort of slide it down the side of the glassware. You can even tilt the glassware so that you're carefully pouring it right on top of the second one. And then the third least dense liquid will go on the very top. So you'll draw in what that looks like, right? So draw some lines where your layers are separated. And it does suggest that you use a different amount of liquid for A, B, and C to kind of keep track of them. And then you'll label it, right? So maybe A was on the bottom, and then C, and then B, right? So make sure you're labeling each layer with the appropriate letter. And then after that, you have added in some colored water, and then you wait to see what happens to the colored water that you add in. And then you can draw what that looks like. You can even color it, right? So if the top layer is blue, you can go ahead and color that blue. And then after that, you're going to stopper and shake, right? You're going to wait a period of time for the liquid to settle, and then determine how many layers you have and try to identify the layers. If two have mixed, which two do you think it is and why? And then, of course, always pay attention to the procedure and making sure to get the appropriate pictures, right? And always have your college ID in those pictures that you're going to submit with your data sheet. Okay, and then we have at the very end the post-lab, right? So the post-lab asks you to think about whether or not the different liquids are miscible or immiscible, right? So, and how do you know? Okay, so use your justification based on the evidence that you have in the lab to say whether or not these liquids were miscible or immiscible. It also asks you to talk about the miscibility of the colored water, right, in each liquid. So we did that in the vials, right, the separate vials. So were those miscible with the colored water or not, right? What is your observation to justify that? And then after that, look at that data table listing the different densities and see if you can identify the liquid. So that should be based on density as well as whether or not it was miscible with water. And then it asks you to do some more calculating of density, right? So we have masses here notice the different precision, right? This has no places after the decimal. This was measured to the 10th place and the 100th place for solid C. And then the volume, right, for each cube. So you're going to calculate the density, and then you're going to draw this pail, right, maybe down here, and it says that you have placed it in, let's see, determine how the following solid blocks will settle upon adding all of the solids to a bucket full of water, right? So if it's less dense than water, you want to show it floating on water. If it's more dense than water, you want to show it sitting at the bottom of the bucket. And then if the density is about the same as water, it should sort of float in the middle, right, of the bucket of water. So it won't be at the top or the bottom. So make sure you're placing those in the right position depending on the density that you calculate. And then don't forget to report your density to the correct number of significant figures and place a box over that. And if you don't know how to report to the correct number of significant figures, or you're really still confused about that, really encourage you to try to come to office hours. Even I know you're at work, but maybe you can take a 5-minute break just to come in, and I can help you with anything that you're struggling with, or send an email or something like that so that I can help you as well. All right, so that is the end of this, and good luck with your experiment.